Hello, everybody. My name is Kevin Kawchak. I'm the founder CEO of ChemicalQDevice, here to tell you today on transitioning from ML to hybrid QML and neuroimaging. So it's this process that we'll be making, especially through 2023. This is episode 55, November 3rd, 2022. So as you can see, it's a big thing for Alzheimer's. So when I say Alzheimer's, I'm talking about neuroimaging, to get better images, for better prediction. And this could be MRI, PET, and or CT. Here's the layout for today. I'm going to focus on 3 articles. So in specific, the first one's ML for Alzheimer's disease. This is kind of like a down-to-earth study. It didn't have a lot of patients. It's using EEG, but it can hit it out of the park. It had high AD accuracy. Article 2 in the middle there, ML for brain diseases, a 2-stage approach. They're wanting to, this is a big study, and this is with many types of neurological disorders. They wanted to ultimately replace a clinical routine that, a prospective, doctor does, so instead do it with this deep neural network. And then the NASA one is a huge paper. It's very long. It's a 10-step process of technology readiness. So we're talking TRLs and then specific ML TRLs. So for more complex systems, it's very thorough. NASA and DARPA have, used it for standards, and also aligns with other healthcare applications as far as other people in specific doing somewhat of a thorough thing to make sure the ML technology is worthy. Now, in this specific paper, this is Article 1. So it's titled The Development of an Automated Machine Learning Pipeline for the Detection of Alzheimer's Disease. And it's in October 2022, so quite recent. So basically what they're finding is a lack of reliable disease endpoints in our biomarkers contribute to less effective Alzheimer's disease therapies. And machine learning used used to analyze EEG, and that's what they're saying, 81% logistic regression. It's a very, with EEG, you're just getting electrical impulses. It's not quite as detailed as MRI or CT or PET scans. But I'll show you a little kind of image that shows, how you can kind of tell the difference between a healthy control and an Alzheimer's disease. So this is a basic process. So it goes everywhere from you have EEG collection, transformation from time to frequency, so on and so forth, to get to feature extraction, selection, and then input into ML. So this is basically the rubric that they created and followed right there. So what they addressed is basically there's disadvantages to the super complex things. So number one, a lack of automation and unbiased removal of artifacts. And the other key with this is many universities, hospitals have EEGs. They're ubiquitous. So that's why they're focusing on this. The trend seems to be more for magnetic information, like, quantum sensing or like, squids, or even, like the functional kind of MRI. And in specific, it's whenever you hear this dependency on high levels of expertise, that's usually the opposite of automation. So they want to take these next steps to get automated. So in 3, and not requiring these huge studies, as with the case of, say, like a deep neural net, which is more opaque in what you can see with it. And also, MRI, CT, and PET scans are physically larger and in more select areas. Now, in using the EEG, they're basically saying it's accurate, quantitative, and that, this is not a new thing. EEG studies and ML it's a very common thing. It's even gone international. Now, the previous ML studies have focused anything from categorization to classification, support vector machines, convolutional neural networks. I'm in the 3rd bullet point here. Linear discriminant analysis, multi-regression linear analysis, And some of the caveats with this or negatives to the EEG study is long epochs, high density EEG systems, high throughput screening, and especially this computational load, you know. So the quantitative analysis of this, basically it's using a low number of channels. And then also with this, there's other studies of this. I've talked about this before. And with authors, basically, this is where the science is. So you have, say, for instance, this AD power spectral density, which is the function of the electrical or potential or voltage, and it's a function of that. And then basically, in specific, their study is based on this: increase in delta and theta bands, decrease in alpha, beta, and gamma. And I'll show you which is which between, say, the healthy control and the Alzheimer's disease. And in the future, they want to combine it with, functional, like these, big imaging with MRIs and so forth. So this is where it's at. So basically, when you're measuring electrical impulses from the brain, it's coming from electrochemical these synapses and neurons in the brain, and you also get magnetic information at that same time that this is measuring electrical. So in the blue line, you see healthy control, and then the Alzheimer's disease, you're seeing this red. So one wouldn't think that you could just, determine Alzheimer's disease, demented or not demented, from a simple EEG study, but this is basically what it's proposing, and, with 80% accuracy approximately. And these are the steps that they went through. So implementation of automatic, artifact removal via support vector machines, a very common method. Number 2, analytical pipeline negates need for high levels of expertise. Number 3, this smaller study, 41 patients. Number 4, PSDs guided by statistics for feature extraction. So the summary basically is this: it's fully automated process for AD based on resting state EEG using low density channel montage, an end-to-end automated analysis pipeline for data processing and statistical guided feature extraction. Now, the pipeline wasn't validated on an external independent data set. It can also, benefit from MRI collaborations, and then it's a relatively small sample set. But nonetheless, it's in scientific reports, it's a Nature paper, kind of interesting. Now, Article 2 is, kind of like the opposite. So it's this comparative analysis. I mean, we're still in the same field, but comparative analysis of machine learning algorithms for multi-syndrome classification of neurodegenerative syndromes. So this is anywhere from AD to Parkinson's. And it's basically trying, in a clinical setting, offer a solution. Now, when you go broad like that, you're losing, your results tend to suffer. So I'll show you those a little bit later. So basically, of these 4 that they use in the second bullet point, it's this deep feed forward neural networks are compared on, on MRI, and they're the ones that did the best. I'll show you, a little bit later how that all wound up. And then it just makes sense. The diseases that have regionally specific and pronounced atrophy patterns are generally better classified. It makes sense. Some diseases are easier to study than others. And I think as a group in their scorings, they were in, this is, I'll get to this first. So this is basically, 800-900, cases here. So you have Alzheimer's disease, frontal temporal disorder, Parkinson's, all the way to healthy controls that was used. So it's a comprehensive study. Now, in literature, the authors have focused on SVM, and it's kind of deep neural networks are usually, thought to be, your best potential to get, your most comprehensive results. At the, it's a more opaque technique than others. So I'll get to that. So similar to the work of radiologists in clinical routine to categorize brain as normal or abnormal, and then to define entities. And then, so you have volumetry data with a single CPU. And this is basically what it's saying, is when you're switching over to raw data, you know, a 12 gigabyte GPU is not in a common laptop or desktop or anything. We might have, you know, 8 gigs of RAM or 16 gigs of RAM. But the whole point of this is basically in these neural networks is you're, you know, really bumping up on and, you know, what you need. And especially for quantum technologies, you know, kind of finding these solutions of not only having CPUs and GPUs and now a QPU, what could that mean in specific processes that use quantum mechanics? So then they say predefined feature extraction might lead to a loss of valuable information. So it's just a limit of the study. And the top chart is the one that's important. So it goes random forest, gradient boosting, support vector machine, and then deep neural network. So the higher, the better. And again, these are generally, you know, 0.496. I believe the scale is 0 to 1. They're deemed as fair. It's a somewhat aggressive study, you know, basically trying to look at all these neurodegenerative diseases and get this, you know, to help doctors out. And you can see this graph is the average training loss, you know, so yellow is loss and then blue is validation loss for deep neural networks. So the conclusions with this is basically with this large data sets, that's kind of where the neural networks shine. The limitation is that this two-stage approach with volumetry calculation classification carries risk of error summation. It's inherent. So the data that you start with has to be very high quality. So future studies, they want to do raw MRI data. So it's the next step up. So you need more computation, all that kind of stuff. More comprehensive balance, and preferably with international colleagues. It's just people's brains think differently in different parts of the world. So test and it's good to, you know, have the collaboration too. And they're also saying, like, you know, this may have been a mistake that they made, is basically, you know, test and validate several methods. Consider the available computing resources first. So once you get into these deep neural networks, these types of things, that it's very computational. Now, this third article, technology readiness levels for machine learning systems, is a very long paper. It goes through, you know, what it all means as far as 0 to 9. And then it keeps going through several examples. So if you can get through it, but it's very, very, so this is a culmination of many things, you know, with machine learning, and I'll get to some of the kind of cool examples, but we're talking, this is used as standards for NASA and DARPA, you know, for robust, reliable, responsible systems. And in specific, you know, becoming more valuable with complex, larger systems and environments, which everybody wants, but these are the steps you have to take in order to prove that they're valid, you know, to use. So this is their flow chart, and they say many stages don't start at TRL 0. These are more like first principles, and in fact, many companies don't even get involved with other startups that have this 0, and then you go 1, 2, 3, all the way up to 9. And I'll go through as far as kind of like some of the highlights with this. It is basically, you know, it's to get these MLs, you know, your products to, you know, industry readiness. So level 1, so, you know, 0's more fundamental, but level 1, goal-oriented research, design and run low-level experiments to analyze specific model or algorithm properties, you know, skipping up to 3, checkpoints towards interoperability, reliability, maintainability, and so forth. Now, in level 5, they say it's really crucial because this is the whole machine learning capability technology. So it signifies the dedication of resources to push the ML technology through productization. So in the startup world, we refer this to as the valley of death. So when you're a little bit further along, you struggle to allocate resources and align roadmaps. So in a lot of these things, it says, if you're going through these strict steps, you know, it can help, you know, because you have all of this data and you know, more organization for your specific project. And again, in level 7, tests that run use case specific critical scenarios. And then level 9 is deployment, where you have continuous monitoring, updating. So here's some cases. So computer vision with real and synthetic. So these synthetics can be GANs, or generative adversarial networks. And then you have 2, accelerating scientific discovery with massive particle physics simulator. So the word alzheimers is simulate, spelled backwards. So you could just see, like, there's been so much work with ML in this case. So also that you could use subsets, and they're saying you don't necessarily for everything need to go through all 9 steps as detailed. So a Google model card for basic image classification, is something. So this is a TRL for level 4, and they put in fake names. Well, actually, I think the A Lab and Gene Renard, but you could attribute this to Apple, founders Wozniak and Jobs. But they say it's supposed to look like this. It's supposed to look very dense, similar to other things that have been, done. Get all the information on the card, spare no white space. So in 2010, NASA, with this, basically said cameras for all-sky meteor surveillance. So this consisted of hundreds of CCTV, and these are off-the-shelf cameras for nighttime meteor capture. So in 2017, update from Frontier Development Lab, and this is automated data processing pipeline, also building on this ML model. Number 3, it's orders of magnitudes of improvements in operational efficiency. Number 4, amateur astronomers were allowed to contribute to the meteor sightings, and then it had a 6-fold global expansion of data capture. Now, this is important for healthcare for many reasons, is that there's been attempts with healthcare, checklists with this RWEs, real world evidence, but they're relatively nascent. And this specific study I'm going to check out further is comprehensive analysis for medical imaging in AI, regulatory recommendations mirroring this, MLTRL. So you have this being developed, deployed, and iterated in many environments, and especially it's for noisy inputs, noisy sensors, all that kind of stuff, and it's to overcome that. So, and we're always going to have some level of noise. I mean, not everything can go. There's shot noise, but below subshot noise, and there's other types of noise as well. But they say it's not to be, okay, I want to do this, I have to follow every one of these specific steps. It's more of a checklist. And it's agreed upon by other people. And it's, with existing software, not necessarily to replace them, but more of like you have cards, like you're 0 through 9. So when you're on step 0, get that card right, advance it to the next step. So it's this progression that you go through. So the data availability is still an issue in anything. So it needs to be very high quality because it goes through all these processes basically. And, with ethics, it's continuously evolving, even with these TRLs as well. Now, Google, there's many other organizations such as Google that have had their hands on, these types of things as far as getting highly organized with ML. And in specific, in the second bullet point here, practical value comes at level transitions, so between 0, 1, 5, 6. Aim is to build reliable systems, and here it is, this key point, with myriad unreliable components, so noisy and faulty sensors, human and AI error, so to account for all that. In the future, they'd like to do, to further understand principle, theoretically grounded and generalizable way of propagating errors and uncertainties downstream and throughout more complex AI systems. Now, I spoke a lot of these. So these are 3 articles on ML. And when you're transitioning into hybrid QML or QML, if you have all quantum components, that it's important to know that, it's a gradual process. There's transfer learning. There's, certain things that have been done already with hybrid QML or QML. Now, I'm going to go through these charts, and in specific, they say, so these are the ones. So most recently, I added this July 2022. It's for breast cancer. And it's for error mitigation, right? So there's just many things that keep, get this continual development in quantum to get the results better. Now, the May 2022 is a big paper. This is Zoran Krunik. He's with Amgen. There's a doctor from IBM that was part of this as well. And basically, it's one of the largest QML experiments done. And they are basically saying empirical quantum computing with quantum support vector machines and for rheumatoid arthritis to get the results. So there's a lot to learn from here. So many people think, oh, I haven't heard anything with quantum and medical or healthcare. It's because the computers aren't awesome yet. Now we have, these kind of forecasts as far as next year's practical quantum computer with NSF. And we have, some presidential support from Biden and Obama, basically going to different, events at IBM or in Chicago. And then we have, the first quantum computer for healthcare being built at the Cleveland Clinic. So, there's steps. And then as far as we have an IBM quantum computer due out this year, 400 something qubits, and everybody's just hoping the error is lower in a lot of these things. But you see in this chart, Alzheimer's, arthritis, heart, brain, basically laying the foundation, the framework for methods and analyses. So when the good hardware hits, there's many people, QML is not a new thing, hybrid QML, the same kind of thing, and I'll show you. So these are more papers as well. So we're talking COVID-19, and actually some of them said that they did have, beyond just promising heart technologies, there's some light in the tunnel, even with specific COVID-19 research with CT images, these types of things, right? So you can get decent results, with simulation or with hardware or with annealing, in some of these things, but you see brain and imaging. Now, in specific, this specific chart, I've talked about some of these, Cleveland Clinic, IBM, we're getting a new healthcare quantum computer. You have quantumalgorithms zoo. So this site was updated for 10 years. The gentleman, Stephen Jordan, he works at Microsoft now. I think he took a year or something off the site. And then as of last month, it's been updated. So that's a good sign, that things, could prospectively start moving quickly, especially with all the kind of like the news for 2023 happening. So the NVIDIA is Quantum and Coda. And then, these are hybrids and basically to help ML workflow. NYU Langone and Fermilab, they have something like 21 organizations partnership with this SQMS, superconducting quantum material science, I believe is what it's called. And basically they're building a quantum computer and quantum sensors to make better MRIs. And then you'll see this June 2022, this is a review of quantum in healthcare this far. So it's not a new thing. It's just people don't hear about this in healthcare as much just because the hardware component is such a big thing. And actually quantum memory too, and quantum sensors, but there's ways, and I'll show you this Google Harvard Caltech paper of overcoming or mitigating some of the error with other quantum technologies. Now, if you want the thorough everything from this is called the Big Table of Quantum Artificial Intelligence from April 2017. As you can see, it starts in 1984 with this QC, which is hybrid quantum classical systems using quantum techniques to solve classical machine learning problems. And you'll see a bunch of these are supervised and QC, but this is you'll see CC, CQ, QC, QQ. So obviously going into a new quantum era, and especially in healthcare, we look for the ones that have a Q in it, either in data or in algorithms. So this is the rest of the table on this slide too. It goes up to 2016. And this, again, this is kind of a lot of things, but they call it the big table. And then the paper was in 2017. Now, for quantum internet, for Alzheimer's data security, it's a huge thing. And what you're likely going to hear about in the news more recently, or I'm sorry, more upcomingly, is basically data security, post-quantum cryptography, attacks from international countries on US, defense using, PQC, QKD. But this is interesting because this is from NIST, an American university, and this is integrated quantum and classical communication links. So from my perspective, we have an advantage going into all this quantum incorporation into quantum internet. And specifically, we have, DCQNet in Washington, D.C. saying we will have a national quantum internet. We have Fermilab and Argonne saying they transmitted both quantum and classical information at the same time. So the advantage, obviously, is we have the fiber optics network that we didn't have before. If you remember your first dial-up, over phone lines, and then just how much faster it was with fiber optics. So not quite sure as far as, what can overlap at the same time between quantum and classical information, but you can kind of get this gist between, quantum computing units, quantum switch, classical edge server it's hybridness, right? And they'll, say a hybrid quantum internet, most people will just drop, or I believe many people will drop the hybrid and just say it's quantum internet, even though a good portion of the components are classical. So here's that. So the cloud in the middle is the previous graphic. And then this is how it relates to, scalable quantum edge computing scenario. So you have classical computing units, quantum processing units, quantum computing units, quantum switches, quantum repeaters. And I've seen other things from other countries that kind of like, validate this as well. And this is basically from NIST. So they're really into quantum, but quantum communication links and classical communication links there. So what's really important is the hardware in quantum computing. And like I said, there's some workarounds with quantum sensing and quantum memory that you can, mitigate the error, basically with other quantum effects and, storing it with, at brief intervals and quantum memory. But ultimately, if the quantum hardware is awesome, even better. So the big thing here is Quantinuum. They announced that you could take an 80 qubit circuit and run it on a 20 quantum 20 qubit quantum computer. And some other things that other technologies have wanted, this is ion trap, is mid-circuit measurement and mid-circuit reset. And going over to Goldman Sachs, this is error mitigation. So you'll see Goldman Sachs mentioned in a lot of these articles as far as, obviously potentially financial support, but this is a lot of it's going to go into the financial industry. Now, this paper on the right is not for the faint of heart. It's basically, it's very technically, difficult to read. But basically, it's saying, using quantum memory, and again, to enable the power of large entangled states. So if you can't get the error right with the computing between quantum sensing and this is quantum memory, it's a huge thing because it's like a buffer, basically. And other papers, such as Los Alamos National Laboratory, found that if you have more quantum components, such as the quantum, not just quantum computing, but quantum sensing, quantum memory, and quantum algorithms, is your chance for quantum advantage are larger. And then IEEE quantum at the bottom, they're basically saying there's already quantum standard efforts and works. So there's no turning back, it doesn't look like. So these are some basics. So I'll put this deck up. And then if you have any questions, this is just general quantum computing. This is the Los Alamos National Laboratory. It's basically saying QML will be the natural model to learn, infer, and make predictions from quantum data. Data from quantum mechanical processes is more likely to see exponential quantum advantage. And then this exponential quantum advantage will come from sample complexity as opposed to time complexity, likely with hidden parameter extraction. And then these are some of the things that will benefit from QML. QML is a very targeted area in quantum technologies. Number one, the hardware, can get better. And then, using other quantum technologies to support it, even during this NISQ period or noisy intermediate scale quantum period. But these are some of the options right there. And then this is a big paper. So in the lower left-hand corner, QML saves a copy of the qubit state and tables it with the next copy, learning about quantum state more quickly. So even with this, the computer they used on this was the Google Quantum Supremacy Computer Sycamore, 53 qubit processor from October 19. And it's using other quantum technologies, including quantum sensing and quantum memory, to kind of pick up the slack to get better results. Ultimately, we don't want any error around, but adding these other quantum technologies are making it better in order to do quantum machine learning. So here's the basically results. So the blue is better on the left, and then you're getting better separation with data on the right. I posted this before. The big key with this is many things in neuroimaging uses machine learning. So that's the call to action, is basically to insert, hybrid QML over these next couple of years with the ChemicalQDevice to get better results, better sensitivity. So this can range anywhere from the quantum sensing itself to the more software approach with QML to get better, so image formation, image computing at these specific steps. So in specific, the research is, quantum will have to, even though it's supported by 21 government institutes, and it's really picking up steam in industry, it's going to have to go through rigors, right? So this is an example of a rigor. So I chose, QML, TRL for stage 5 here. And, basically going through these things, and the call to action for the startup is basically to collaborate with medical collaborators that have, quality neuroimaging data. And I posted this last week. So this is basically, there's going to be a progression, so ultimately, on the most fundamental level of making neuroimaging better, you have detection. So when you have a diamond quantum sensor, these types of things. There's quantum imaging, so quantum ghost imaging, subshot noise, these types of things. Quantum image processing, I believe, is more time complexity, QML, optimizing quantum circuits, and then GANs. So you're going to see these generative adversarial networks with, say, 90% artificial data or simulated data. When they get more validated in healthcare, is going to basically open up bigger data sets, right? Because that's what everybody wants, even if it was only trained from like 10% real data. And then, at the end is basically, having these better neuroimages, and then creating models at each site and sending them up for federation. So this is quantum machine learning circuit optimization, another approach to take for the startup. And this is the crux of it too. So this is basically medical image processing or neuroimaging processing using quantum technologies. So a couple options in the first one, formation, where you have more detection, and then reconstruction algorithms. And then option 2, enhancement visualization, that's more computing, image computing. These are sensor options right here. And again, this QPSD is very promising because it offers, noise reduction even for vector magnetometry, which is, like an MEG measuring magnetic information from the brain. And then other papers on the bottom. The bottom left is very thorough for a rat's heart, and then other ones kind of with ML and measuring all frequencies. So this is an example of using quantum sensing algorithm computing to make quantum computing better. It may be more of a thing where this is being done in industry and utilizing these sensor memory kind of enhanced quantum sensors to get better results in imaging. And then the market for medical imaging is quite big. You rarely see anything above 30%, so saying 45%. Neurology is the principal component, and this is compounding annual growth rate. Compounding for quantum computing, 33%. And then, so for next year, 2023, we expect this practical quantum computer. Here's recent decks. So there's 8 total. So there's 2's not shown here. that you can look, and they're just like this, articles and then startup. And this is the ChemicalQDevice mission statement: is to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and or resolution, leading to advanced prediction in neuroradiology in Alzheimer's disease. So this can include quantum sensing, quantum algorithms, quantum computing, and even quantum memory. Now, the roadmap is for next year is to develop QML neuroimaging improvements utilizing medical research collaborators. So these are people in the medical field that have the neuroimaging data. Their tasks are either too slow or they're not possible to incorporate. So anywhere from better detection all the way through, image computing. So going back to Alzheimer's, so I've done, two of the papers today were Alzheimer's based. This is an updated view of the mechanism, with Alzheimer's in the brain. It's not what I learned about when I was in neurochemistry at the university. Here's some examples of papers. So it's just interesting to see what's coming out in the news. And these are the organizations to support. I volunteered at a couple events in town here in San Diego, and it's just to hear other caretakers talk about, it's just such a hard time, especially if they have a parent die and then another one passes away within a month. What can be done with neuroimaging in a lot of these cases to make prediction better and kind of like that care better at that time of life. And that's that. So I wanted to go over, okay, so I have this. Is basically, there's a number of feedback. So what is the benefit of QML and Alzheimer's disease? One individual said early AD diagnosis. Somebody says to mine big data, which is kind of interesting. Another person said data analysis, another person faster detection, another person drug discovery, another person better imaging, and another person image processing. So there's that. I'm going to open up for questions or comments. So we'll get chat. Unmute. So you feel free to unmute or come on. And then basically, yeah, I'd be interested as far as, your quantum approach or your quantum take to a lot of these, and especially going into medical fields, especially if you have Alzheimer's disease, these types of things. And then, so we have a number of people returning. I see George and Ron. Feel free to unmute. So this is a new time, usually at 6 p.m. PDT, and I appreciate the flexibility and people still coming on. I see America, who I believe met at a tech coffee in San Diego. So if I mention your name, you can come on, or anybody can come on. But it's good to see many people returning from Kino to Sandeep. So you should be able to. And then, so I opened up the chat there. So anything, feel free to ask questions in the chat as well. And yeah, it's just an exciting time, especially in healthcare. The big announcement with IBM and Cleveland Clinic, previously they announced a 10-year partnership, which includes quantum and other technologies too. Now, to see a quantum computer being built at Cleveland Clinic in the hospital, I would assume that we're a little bit past that phase of having hundreds of quantum computers at IBM or anywhere in the cloud, for just research, right? So a lot of these things, you have to look at closely, and especially with Biden, going to IBM. This is, I think, like 3 weeks ago now, and basically saying they take a picture in front of the quantum computer with American flag in the background, and then Biden's making very favorable quotes as far as this part of New York being a hub for quantum computing. Go ahead, Ron.
I just wanted to make a comment. During your presentation, you were referring to the difficulty in finding GPUs of a certain size. I have to agree with the availability, but the product is definitely out there. For example, you can easily find 16 gigabyte GDDR6 based NVIDIA cards using the RTX 5000 family, which is an impressive a very impressive GPU, over 3,000 CUDA cores, almost 400 tensor cores. So these things are generally in the $1,500 to $2,000 range for just the card. So it's not. You were correct in saying not every desktop has one, but for a few $1,000s, you can probably build a machine, and even with two of these cards. And there are motherboards available today that can have core memory as high as 128 gig. So if you have a budget, $5,000-$6,000, you could probably build your own desktop GPU-based ML machine for the classical side of the hybrid QML picture.
Wow, that's amazing. I remember in previous discussions you would bring that up as far as the GPU being too powerful and trying to find applications for it. And in specific, like NVIDIA's the leader, if not one of the leaders in GPUs, and just combining it with, say, for instance, a QPU that can do things different than a GPU. And 120.
So the card I'm referencing is something that's available on the street, or for a commercial, not necessarily professional. It does say, I mean, based on these numbers, this may not be their NVIDIA's latest and greatest H chip, I think they call it. But still, I mean, 3,000 CUDA cores, that's a lot of number crunching. And yeah, the whole thing that NVIDIA is fighting these days is they can build GPUs that are so big and powerful that you just don't have the bus bandwidth to pump data at it fast enough to keep all the cores busy. So I'm suspecting that's why they have, the H chip is, I haven't really seen it announced on commercial products yet, because I think they're still probably pushing their drivers. They're trying to squeeze every amount of performance out of the drivers, and so that they can keep all of those cores busy.
Yeah, I appreciate that. That's like, I'm assuming you're aiming something bigger than like a PCI Express 16. I know I haven't been following it too closely, but it's very interesting because I've heard other experts say that, that we'll remain having a CPU, and then the GPU, and then the QPU, quantum processing unit, will act more like the GPU. And then what areas of quantum, and we're talking about very specific things that could entail, not only internet, but on that more kind of like circuit board scale, quantum this, especially hybrids too. So yeah, it's very interesting. I mean, I guess the biggest thing I saw an NVIDIA that it was maybe like a quarterly update or something, but the videos that they show are very advanced, and I think the whole thing is that they're real time. Say, for instance, for computer gaming, as opposed to it just being just a video. It's getting that fast, and it's really quite something. Like it's getting harder and harder to tell if something was just recorded video on a camera or if you're playing in real time. And I'd be interested if anybody else has anything. So I see George is back on. Anybody else that we haven't heard from today? And feel free to unmute, or you can come on. Go ahead, George.
I think the potential use of cheap ARM or other RISC CPUs combined with a better bus architecture, which Ron mentioned, could do a lot of parallel computing cheap. The problem with, as he mentioned, is to do it on a laptop or desktop, you need a high quality bus architecture like PCI Express or something. But even if you put then multiple CPUs, GPUs, and a lot of memory on the bus, we really don't have good parallel architectures to take advantage of all of that. I think actually a lot more work needs to be done on the algorithm side. And I think that will also apply to quantum, as I see you're going to have the same bottleneck of getting classical data into the QPU and quantum data back out. That's going to be the bottleneck.
Yeah, that's not the point. You know, the more research this, the more they're putting Qs in the front of things. So if it's like a QR or a Q PCI Express, a Q PCI, I don't, you know, but it'll be interesting because as far as the startup, mostly interested in this whole transitioning from ML to QML in this medical setup that it's high regulatory. So, you know, that's the big issue is like, you know, like how will this all play out? You know, and again, we have things supporting it as far as, you know, say for the instance, these 9 IEEE standards, those types of things, and then the 21 government institutes that all relate to quantum. So yeah, as far as like, you know, it's a transition for a lot of these things, and some will take more time to get approval. Say, for instance, if it's, you know, directly relating to patient data, and I know they use for CT scans, so this is computed tomography. This is basically, they already use diamond sensors or diamond quantum sensors. Like a CT basically shines X-ray through a patient, and then you detect it, and they're already using arrays of diamond sensors there. So that part might not be as hard, but something like a qgan, so you're coming from, you know, both simulated and real images, you know, to basically say, okay, we can use this and to make large image data sets. That might take longer, you know, and especially, you know, add complexity with generator and a discriminator, you know, now inside of a quantum computer, you know, with individual qubits. But yeah, it'd be very interesting to see how a lot of this plays out from kind of like that more fundamental, you know, silicon, you know, like if we have, and especially if we have silicon spin qubits on the actual, you know, dies to, you know, saying, okay, we did this and this and this in quantum. Can we now use this for this specific, you know, high regulation area?
I have another question about medical data and modeling in general. It's not my area, but I'm wondering how close that field across imaging and other kinds of data, how close that is to large models. Like in NLP, you have like GPT type models where you can use pre-trained data and do transfer learning to assemble your model instead of training from scratch.
Right. Yeah. So I've gone over, it was a good paper on transfer learning. And it's basically, so for everybody that doesn't know, so NLP means natural language processing. And then, so for this pre-trained data, they achieved, it was in one of the spreadsheets that I put up. And basically they're saying, so transfer learning is basically for fine tuning. So yes, quantum has already been used for fine tuning Alzheimer's data. And then it's not clinical, but in clinical meaning to the point where it can be used in hospitals like routinely. But yeah, there's transfer learning comes up a lot with quantum, just because it's just basically insert quantum here at this step as opposed to, you know, a full conventional setup. And, you know, some other areas, so if we already have CT imaging that uses diamond quantum sensors to receive, you know, the reflection off the patient, is that maybe that might not be such a hard step to use diamond quantum sensors now for, you know, parts of MRI or, you know, as a replacement for squids. Squids are superconducting quantum, you know, devices, or OPMs, which are promising, and now diamond quantum sensors. So it really, really depends on the application and in specific, you know, what the end result with a technology that's not as established will be. you know, if we insert quantum here. But yeah, it's hard to tell as far as the timeline, and that's the ultimate thing is, you know, can you use it, you know, clinically? And like I said, as far as some of the sensing goes, it has, and maybe the quantum computing, you know, especially the many people knowing that it has error, you know, and then quantum memory, it's a new type of memory, you know, so it just takes time. It takes time to go through all the steps.
Yeah, you've mentioned the quantum sensing, and I find that very exciting, and I feel that in technical and engineering terms, it's much further along than quantum computing.
Yeah, and you're saying today's like conventional is further along?
No, I mean, the things you've mentioned, like diamonds, quantum sensors, and so forth. I think in general, my impression is that everything that's more photonic based on light rather than on electrons is further along and more stable at this point in time.
Yeah, and that's interesting that you brought that up. Obviously, the 3 Nobel Prizes for physics this year went for photons and quantum mechanics in specific. You know, these are the people that helped, you know, from anywhere understanding entanglement. A lot of times the awards are lifetime, like kind of like career achievement awards. But photonics is interesting because it's kind of like it's, you know, we have Xanadu saying that you could do a task in 36 microseconds instead of 9,000 years from June 1st. And then I don't know how much as far as it translates, because in ion trap and gate-based superconducting qubits, it's basically, those are gate-based, you know, and most of the things that I come across are, you know, for gate-based quantum computers. And then neutral atom, you know, actually just a big funding round. I think it's 100 million plus for cold quanta there in Colorado. But yeah, it's interesting how it'll all play out, because I've heard of them making things, I believe it was photonics, more gate-like, but how does that compare to all these decades of research? We saw the big table of quantum artificial intelligence, you know, 1994, basically, a lot of these, the algorithms starting and, you know, those types of things. And people thinking all along the way we'd have a better quantum computer, even as soon as like 2017. So there's just so much out there, as even when you look at circuits and a circuit optimization, because on a faulty quantum computer today, it just makes more sense to optimize the circuit before you run anything. In a previous discussion, there's these KNNs, and they're optimizing these KNNs to, you know, from here down to here, right? Like 50% less gates, all that kind of stuff. But that's just kind of what I see. I mean, I could be wrong, but like, as far as what I've seen is there's years and years of people thinking that the next algorithm they make, such as like quantum algorithms do, and the gentleman, Stephen Jordan, taking a year off and then coming back last month, that kind of shows things as far as the industry's, you know, now all these things that he's been posting on his websites, you know, people are going to be, you know, going through the whole QMLs and, you know, the polynomial and super polynomial and exponential, you know, algorithms. And it's basically references. He references all these things. Yeah, but that's just what I see. I hadn't really heard that case as far as like what's been done, and especially with Qiskit being so big with IBM, as far as doing quantum computing on a non-gate base, unless it was they make a potential huge breakthrough, you know, in photonics or neutral atom. But yeah, it's just, if anybody has any comment on that, especially as it's going into fields, high regulatory fields such as medical, you know, that needs to see things exist for several years before they go clinical.
Yeah, I think what I was getting at is that it's going to be a long time before super cool technology is going to be in every doctor's offices.
Well, you know, they say most of this in the next several years will be in the cloud. So you're, you know, more awesome quantum computers than they are today. you know, for Briquette to Microsoft to Google Cloud. And I think IBM just ordered a brand new dilution refrigerator, like a full out room, like this massive kind of thing. So they're really doubling down on their own technology. So, and then are there any other questions or comments? Feel free. So I saw something from Kino. So AlphaFold structure, maybe yeah. So if you have a specific paper, I could take a look at it, Kino. Now the thing, so Sandeep, you said qgans. Feel free to come on to explain if he's still here. But basically, I've been covering on the qgans, and then the qgans is basically you have your generator, which takes random noise, and then you have real images, and they both go into a generator, or they go into a discriminator, and it's iterative. So this 90% fake data combined with the real data over the course of time, the discriminator has a harder and harder time telling if the image is real or not, just because, you know, it knows from the first few cycles real, and then it gets better with the synthetic data as it goes along. And then all of that's heading towards, you know, qgan, which is basically in staff notation for quantum, you know, this qubit 0, 1, 2, 3, 4, you know, is for the discriminator, and then the next several qubits is for the generator kind of thing. Okay, yeah, entangled quantum. Okay, GAN, that's interesting. Yeah, if you have a link with that, Sandy, feel free to post it. I've seen other things as you know, relying on entanglement, and I think I might actually have that paper. It's put away right now. But yeah, any other questions or comments? I appreciate people coming on. You know, there's other people we haven't heard from, so, you know, feel free to, awesome. Yeah, so feel free to put your LinkedIns. And then, so this is a community too. And at that same time, we're all have been growing together. I just remember, you know, the uncertainty of quantum wasn't quite high as it is now, you know, basically having presidential support with it. And the dollar's getting so high, you know, we're talking billions now. Back in October, you know, a little over a year ago, October 1st, IonQ, you know, published that they IPO'd for, you know, $2 billion. And then 6 days later, Rigetti announced that they were making plans to go public. So we've had 3, you know, pure play, meaning that's the only thing they do is quantum, hardware manufacturers, so D-Wave, IonQ, and Rigetti, that are $1 billion or plus, you know. So yeah, it's an exciting, fascinating field. And, you know, just to see kind of these recent developments, and we'll hit something like the June 1st, you know, photonics, you know, with some promising things, 36 microseconds instead of 9,000 a year. Now, the next day on June 2nd, they announced that Classic would, you know, be having this, their platform, their quantum algorithm platform on AWS. So this, I believe, and this is that whole discussion is, you know, not needing experts and becoming more automated. We're starting to see these things in quantum, you know, circuit, you know, gates, all these types of things, to make it easier on an average programmer, as opposed to somebody that went to school for 4 years or even 5 years for your post, you know, PhD, then postdoc, those types of things. But yeah, if there's anything else, and then I do see some new faces, a pretty good turnout this week. I switched to 9 a.m. to catch people more from East Coast and then in UK. So if you're based kind of internationally, I'd like to hear from you as well. And yeah, any other last questions or comments? This has been episode 55, November 3rd, 2022. And then if not, so Ron put his LinkedIn in there. Sandeep, I have you too. So these are people, so Ron and Sandeep have been showing up quite frequently. And then, so feel free to add them. on LinkedIn. And then, like I said, I'm interested about the quantum entanglement GANs. And then I might, like I said, I might actually have that. But, you know, we can connect on LinkedIn. And then, yeah, just for everybody else, just keep at it. You know, we're kind of in a good mode right now. There's a little bit of uncertainty as far as how much error correction we will see for next year. But basically, you know, things are on the up and up. You know, you really can't argue with the last months of news. So, you know, and I'm talking about like the presidential visits. So, oh, and then Sandeep said he's writing on that too. So I'm assuming you're talking about the quantum entanglement GANs. That's awesome. Yeah. And again, like any links that you could share, because this sounds like all good news. And any links you could share either on the discussion or you could reach out on LinkedIn. If not, again, this is episode 55. My name is Kevin Kawchak, I'm founder CEO of ChemicalQDevice, looking for collaborators in medical, in specific neuroimaging data, and then anywhere from sensing to using QML, better with you know, image computing, those types of things. So that's awesome that Sandeep says he's writing a thesis on that. So, you know, yeah, so look forward to your developments there. I appreciate everybody coming on. Have a good rest of your day. Take care. Goodbye.